and hopefully also introduce some new things, well, not new things, but just like kind of get your brain back in astronomy mode. I also want to talk a little bit about the fact that I think I fixed the photometry project, so I can show you guys a little bit more about what that will look like and give you just some instructions, but that'll be at the end. So hopefully this comic isn't too much in poor taste, but I thought it was funny. So, and we're making a space ladder, so it works. Today is going to be, I'm going to try to this is going to be might be a bit of a struggle, but I want to have you guys do as much of this as possible with just me here to kind of guide you along when you get stuck. So what that means, it seems like you guys are pretty okay with talking to each other, but I'm going to ask questions and there will be awkward silences if no one answers because I'm going to wait until someone answers. So there might be some awkward silences today, but today's going to be a little bit more discussion-y. So that being said, let's start climbing the ladder. So the first step we need to do is we need to calculate the distance to the sun. So what could we do? What are some ways that we can figure out what the distance to the sun is for our step one?
We could use apparent and actual magnitude and use that 5 log 5 plus the fact that there's nominal extinction to calculate it, so using luminosity.
Okay.
We could use some Kepler rules, figure out if we know masses, then we could get a distance.
Yeah, so we've got Kepler and we've got a luminosity. Luminosity is going to be a bit tricky because I think you need the distance to the sun to calibrate that, because absolute magnitudes are based on a 10 parsec scale and we don't know the distance of a parsec yet. So we are very much at ground zero. Luckily we can do, yeah, I guess Earth. We haven't taken our first step. So we can use some Kepler's law. So if we know the rotation periods, yes, if we don't yet know the masses, but we're going to use the fact that we know the rotation period. So we will need, we've kind of got Kepler's original law. Sorry, I'm kind of rambling. We're going to move our way in. Was that P squared is proportional to A cubed. So we're going to use that fact. If we know all of our P's and we know kind of the ratios of, we can use that to get ratios of A. So if I can measure how long it takes Venus to go around the sun, I can figure out how many AU, how many distances to the sun it is between Venus and the sun and between Earth and the sun. So then we can get kind of a scale even if we don't know Venus's mass. So we're going to use that. So if we know we're getting closer, we know that we can get a fraction, we can get kind of these fractions, and we're going to use that somehow to get a distance to the sun. Does anyone have any ideas? There's one more thing we need to think about.
This is sort of cheating because I remember doing this, but you can also like bounce a radio signal off of Venus to get the distance to Venus, I remember.
Absolutely. So that's the one thing we can do. We can figure out if you know distance from Earth to Venus, then we can plug that into our fraction from Kepler's laws, and we can get a distance to the sun. So that's kind of how it's done now. Back in, before there was radar that we could bounce off of Venus, you can also use transits. So we can look at the transit of either Mercury or Venus across the sun. It has to be Mercury or Venus because the other planets won't transit because they're outside. And you can use timing of these transits with Kepler's third law. as well as parallax to figure out the timing. So I'm going to show that again. Oops. So what you're doing, if you can observe the transit of Venus from 2 locations on Earth, then you can use the difference of position on the sun and really careful timing in order to figure out the distance from Venus to the Earth, and essentially just use parallax along with our Kepler's laws, where we knew that fraction of an AU that Venus is sitting at to get the distance to Venus, the distance to the sun. A little bit of a kind of tangent, because I think it's kind of crazy, but this was originally done in the 1700s. So James Cook went to Tahiti and measured the transit there so they could compare to people in Spain and England. So they had their 2 locations, Tahiti and Spain. It took about, I think it was 8 months for him to sail to Tahiti. So they had to be really prepared. And Venus transits once, and then it's again in 8 years, and then it's 120 years till it does it again. So they knew that like they had to get it right, or they weren't going to know the distance to the Earth in their lifetimes. So at this point in time, it's like it was essentially like going to Mars when he sailed down there. Half of his crew died trying to get to Tahiti. They also used it as an opportunity to test treatments for scurvy. So they had to eat all this gross stuff. I think some of it like sauerkraut. He would like force his crew to like eat sauerkraut for like days straight so they could see if they could survive scurvy. And he would whip them if they refused. So solid trip. He did better than, there was another astronomer from Spain. His name starts with a G and it is escaping me at the moment. But this astronomer went down somewhere, oh gosh, again, I looked this up, somewhere in Africa. And he went the first time and he missed it because they told him he wasn't allowed to be there. So he decided to just live there for 8 years and wait for the next transit once he got permission to be there. And 8 years later, he went to observe the transit and it was too cloudy, so he missed it. So he spent 8 years of his life waiting for this transit and did not see it. So this original, the James Cook and his expedition to Tahiti, they did actually see it. So, but if you read all their notes, they were more excited about getting to Tahiti and like seeing this new area than they were about seeing the transit of Venus, but they were able to get a measurement of the distance to the sun and get our kind of step 1 on the distance ladder using parallax along with Kepler's laws. So we have our distance to the sun, we have our rung 1. Does anyone have any questions about any of that rambliness? Okay, so once we know the distance to the sun, we can move on to our step 2. I'm not going to tell you what it is yet. We want to find the distance to nearby stars. What do we do?
Is this where we use parallax?
Yep. So once you know your distance to the sun, we know our baseline as we move around the Earth. So we know that kind of, you know, the joke, the whole, if you blink your eyes, your thumb moves. We need to know the distance between our 2 eyeballs, which are the Earth in August and in February, so 6 months apart. So we have our 2 positions. We know that baseline of our triangle once we know the distance to the Earth. So we can use that to look for shifts in the stars and measure parallax. So I had you guys read a little bit about Gaia to talk about parallax, because Gaia is pretty amazing and is a new mission that I think just should be on your radar. The Gaia collaboration is putting out data pretty regularly. You get a new paper from Gaia if you watch the archive. So it's just something to kind of know about, where they're measuring the parallax, they're measuring the proper motion to just billions of stars, both in the Milky Way and in the LMC and SMC. So I opened this. This is a little way where you can kind of play around with some of their data on this website. This is just a heat map showing kind of where they have more sources. So what you can see is there are more stars in the plane of the Milky Way because there are just more stars in the plane of the Milky Way. But you can also kind of see in the bulge, there's a lot more. We can use kind of the motions of, in a galactic perspective, we can use the motions of stars that Gaia looks at to try to get some ideas about stellar streams going around the Milky Way. So where there might be, maybe there was a dwarf galaxy that got pulled apart. If we see a ton of stars all moving with a similar velocity on a slightly weird trajectory, that might tell us that there's a stellar stream. Another thing I think is kind of cool is that you can see the SMC and the LMC in Gaia as well. So they're getting really precise distances to the LMC and the SMC, which is helping us calibrate some of our other distance modulus, or not distance modulus, but distance ladder steps as well. So Gaia is just a pretty incredible project. Kind of fun on this webpage. You can also just make all the kind of plots you want. So I plotted, we'll talk about galactic latitude and longitude soon. No one really uses them, but it's good to know. But I plotted galactic longitude, yes, which is kind of position in the plane of the Milky Way versus the radial velocity measurement for Gaia. And you can kind of see some trends. There's definitely something going on here, I would say, but that might be an indication, again, that maybe there was a stellar stream. So Gaia is getting very precise parallax. I think they measure the motion of stars down to the micro arc second. So just a really cool project. I also made a little HR diagram where you can kind of see different turnoff points, which indicate different populations of stars that Gaia is getting as well. So just a cool project that has to do with parallax and measuring distances. I can also make, you can go here. There are all kind of plots I can make. Does anyone have a request for a plot? I'll just say that, yeah, like I said, I had you read about Gaia because it's a good thing to know about, since it is just a huge source of data moving forward, and it fits on our distance ladder. Now, so, okay. Once we know distances to stars, we can start thinking about distances to star clusters. Things where it's maybe they're too far to get a parallax measurement, but maybe the nearby ones we can get a parallax measurement and use that to calibrate further distances. So what might be my next steps-ish on my distance ladder? We're thinking about distances to stars and star clusters, eventually other galaxies as well.
So is this when we would do what Sabrina was saying with the luminosities and magnitudes?
So close. I didn't actually put the distance modulus in my distance ladder. I think that fits into this step because it is kind of thinking about, I don't want to say this word yet, but using luminosities as a way of calibrating distance. So what would be another way? If we...
Can you use variable stars? Is that...
Yes. So what are what type of variable stars?
The Cepheid?
So yeah, we could use Cepheids, and Cepheids are sometimes called a... I'm kind of doing leading questions.
Standard candle?
Yes. So our next step is gonna be looking at some standard candles. Cepheids are one of them. I also wanted to highlight the fact that you can also use the tip of the red giant branch as a standard candle. That was enough time to get at least most of your thoughts out. Erin, can I pick on you? You had a whiteboard, so I was wondering if you'd be willing to share with the... You're muted. Sorry, Erin.
I don't know if you can see this very well.
Let me stop my share. There.
Did you yeah, did you want me to point something?
No, I think, can you just walk us through what did your group talk about?
So we've got luminosity, magnitude on the y axes, and then like temperature or like spectral type, like OBA of GKM, on the horizontal axis. And we got the main sequence here, and then like white dwarfs down here, like red giants up here. There's like I forget what it's called, the path to becoming a red giant, like the helium flash, the horizontal branch, and the asymptotic giant branch. And then I did like the instability strip. I'm not sure if I drew it in the right place, but
That's,
somewhere there.
yeah, that's great. Does anyone from any other group have anything their group discussed that they think should be there? Honestly, like, this is beautiful. You guys all, HR diagrams, obviously, super useful for talking about stars. So we're not going to talk about them a ton in this course, but it's good to just kind of remember what's going on with them and just kind of get that, since they are really key to talking about stellar evolution, especially. So we'll get, but the big thing is I really like you put that little flash for your helium flash. So in our red giants, I'm gonna go back to sharing my screen. The nice thing about the tip of the red giant branch is that it kind of happens around the same luminosity, no matter what your age of stars are, so or size of stars. So the big stars kind of go off and they do this really fast. They turn off and you get they go supernova, or they turn into neutron stars or whatever else. But if you are low enough, pretty much any group of stars is going to have some stars that are small enough that they will go up the red giant branch. And when they get to that helium flash, it's always going to happen pretty close. Like, there's a bit of fuzz, but it's going to happen around the same luminosity. So we can use that kind of as a standard candle. It's not super precise, but it's one way to get a standard candle to nearby star clusters, is to look for that tip of the red giant branch where it's kind of peaking, and use the shape of the CMD to find a absolute luminosity or an absolute magnitude, and then compare that to your apparent magnitude. So it's with the distance modulus, we're kind of combining distance modulus and our standard candles to get distances. So what Sabrina said, sorry, I had to flash through my things, get my names right still, but merging that together with things where we will know an absolute magnitude. So that's one. The other thing Skylar mentioned is that we can also use Cepheid variables and the Leavitt law, because Cepheid variables, the brightness of a Cepheid variable is proportional to its period. So we can watch it, measure the period, we know the period, we know the luminosity, we can compare the actual luminosity to the observed luminosity, the absolute magnitude to the apparent magnitude, and get a distance. So those are kind of two big standard candles. I want to point out that I did call it the Leavitt law because I wanted to take a little bit of time to just highlight the fact that it was Henrietta Leavitt who came up with this, and she was a low-paid, not professional astronomer working at Harvard as one of the Harvard computers, but just also with a bunch of other women like Annie Jump Cannon, who was also pretty monumental in figuring out those stellar types that you guys all wrote out, the OBG, reorganizing them so they made more sense. So originally they were all based on the size of the hydrogen emission from a star, or the dip from the hydrogen. That's why A, so it was A, B, and then they skipped a bunch for some reason, and then kind of went on based on those and other spectral emission features. But she was able to look at these spectra and order them based on temperature and figure out that you do get these nice kind of trends. So I think I sent you guys an article about the Harvard computers, as well as one about Cecile Payne Gaps. I'm pronouncing her name wrong, but just some of the early women who maybe, especially like Cecile Payne Gaps, I hadn't really heard of until I really looked for female astronomers, but her work showed that stars were made out of hydrogen mostly, which is pretty dang important for understanding what's going on in stars. So just making sure that these are names that we've seen and we've heard of, and we're acknowledging their work. Wonder, like, is there anyone else? Are there people who, maybe astronomers who are important to you guys for whatever reason? Like, these are some that are important to me, I guess I should say.
I like Tycho because I think he's funny. Like, just his entire life is funny.
My favorite day is talking with the 110 students about, he's like, yeah, and he also had a gold nose, except it might have been silver. We don't really know. We're thinking about exhuming his corpse, but you know, and his moose, it was a moose. They sometimes call it an elk, but in Europe they call moose elk, and he got drunk and fell down the stairs and died. Yeah, you know, no problem. Yeah. The other thing I want to, sorry, like, maybe this is a little downer note, but I also wanted to kind of use this to say that astronomy is getting better in terms of women getting degrees in astronomy, but we're still not equal to some other places. So in this graph that I pulled from AIP, astronomy is this purple line. They're very chunky, but we kind of went up for a while, and now we're kind of going back down. Computer science is not doing great, which I think is really interesting, because computer science used to be better when computing was kind of thought of as women's work, and now it's not, because like computers are more, it's just interesting how that's evolved over time. Biology always does really well, which is interesting. Chemistry does fairly well, and then physics and engineering are down here. Maybe slowly increasing, but just kind of chugging along. This, of course, we also can see, if you look at non-white races in physics, there is some change, but it's slow and it's not exactly what you might hope. So this is a physics study looking at African American and Hispanic American folks getting bachelor's degrees in physics specifically, from 1995 to 2016. And there's some change, but again, it might not be. And this is not a percent, it's a number. Just kind of another thing that's kind of interesting. So, and the last one I also pulled is for Native Americans. And again, this is physics. And this is not a percent, it's a number. So especially if we look at Indigenous females, there's not a lot getting physics PhDs for some reason. So I know a little bit about what the AAS is doing to try to change things, but I think it's just, as you guys move on in your careers, something to consider. And I don't know if anyone else has thoughts about how we can make our fields more inclusive. I would love to hear them.
Wait, I have a quick question. Is that like literally like number of people, like 5 people?
In
Wow.
the 6 years, 5 Native Americans earned a PhD in physics.
How many people in general earn PhDs?
So I don't actually
Relative
know
to that number. I don't really know.
I don't know it off the top of my head, but it's, I think this is just for America, and I think it's hundreds to hundreds per year, I think, per year, again, so not per 6 years.
Yeah, very small.
So I just looked it up, and American Physical Society said in 1 year there were 1,700 doctorates awarded. So not hundreds, thousands.
Yeah. So this is a very small, and indigenous populations have been one that I think the AAS has been specifically reaching out towards, which is great, but it's also a group that, again, living in Wyoming, it's one that we try to reach out to, but there are a lot of barriers there. So figuring out the best ways to get outreach to a reservation and also make Native students feel comfortable in your classroom can have extra challenges. And also, I didn't open this because I'm dumb. This is one of a place I like to send students to on occasion, but there's a project called the SACNAS Biography Project that is working to highlight some underrepresented minorities in STEM, and you can sort them based on either their specialty or their ethnicity. So if you wanted to look for an astronomer or someone who maybe you could talk to or learn about their research, this is a really good resource I like to point people towards. It just has some stuff about their lives and just really trying to highlight the different work that is happening. So. That's it. Like, I'm gonna ask this question now, and like, if people have thoughts or feelings, but what are, because I've struggled with this a lot, but does anyone have like a strong opinion about the TMT being built on Mauna Kea? Sorry to just draw, but I think it's something that like, at the past few AASs, so the meetings for the American Astronomical Society, they've really highlighted some of the work that they have done on Mauna Kea to try to involve indigenous knowledge with astronomy. So like Umeamea, they consulted with a bunch of indigenous leaders about how they should name Umeamea when it came through. And so it's Native Hawaiian for visitor from a distant land, I believe. So just kind of like cool. There are moves happening, and there's a summer program where they work with Native students to teach both the indigenous language along with astronomy at the same time. And so they get to name an asteroid at the end and think about why naming is important and how to use the native language to do that. I think it's really cool. But yeah, I'll try not to. I just wanted to point these things out in this class since I think it's an important thing to consider, even though it's not galactic astronomy. Oops. Okay, so back to the distance ladder, just a little diversion there. Our next step, I guess I kind of gave it away, but the next step is going to be type 1a supernova. So this is another one of our standard candles, but it's going to be brighter than the Cepheids. So Cepheids get us to LMC and to Andromeda. So nearby galaxies with Cepheids, type 1a supernova are going to get us to not the most distant galaxies, but at least kind of one step further, since they are bright enough that they can be observed at a pretty good distance. Can someone tell me what's the difference between a type 1 and a type 2 supernova, specifically type 1a?
Is that on type 2 there's no hydrogen in the spectra?
Yes, so that's the official classification. And how do we get type 1a versus type 2?
Type 1A, is type 1A the one with white dwarf and like another star and the white dwarf steals some mass and it pushes it over the limit.
Yep, perfect. So our 1A are white dwarfs if they were in a binary and the other star becomes a red giant and overfills its Roche lobe, so it's kind of putting mass off that it's not, that gets sucked onto the white dwarf. The white dwarf can go over the 1.4 solar masses of the Chandrasekhar limit, and when it does that, it explodes. And the nice thing is because there's that limit-ish, they all explode with the same luminosity. So if we can fit a light curve, we can find that peak, and we'll know, we're going to have a standard candle where we know the luminosity and we observe the luminosity or observe the flux observed and compared to the known, and we can find a distance. Oops, I went too fast. So these are really important for cosmology. This is like kind of hints at our next step as well, but if you look at distance versus brightness, you can use where supernovas are falling to kind of figure out what's going on in the universe. So this was won the Nobel Prize in 2001, I think. Adam Rees, 1991, 1999. Sorry, I just wrote a little bit of a paper about this, so again, I should know. It was Rees, Perlmutter, and Schmidt, I think, who got the Nobel Prize for finding the supernova. Were looking dimmer than you would expect for a universe made of only matter. So that's kind of what's happening here. They're at higher magnitudes, so fainter than you would expect as you move forward more distant, which tells us our universe is not only expanding, it's expanding at an accelerating rate. So that was kind of the big thing with this. And then it's one of those ways that we can kind of figure out what the universe is made of. So we've got a few different models here for different amounts of matter and dark energy, all dark energy, 50-50, all matter, and then something weird going on with dark energy over there. Different forms of dark energy, but what we can see is that we're kind of between the all dark energy and the 50-50, which is probably something you remember from the 170s. We're about 23 to 27% matter, and then the rest is all dark energy with a teeny little bit stored in photon energy or radiation energy, but not much anymore. And that's something that's more on the cosmology side, so we're not gonna dig too much into that this semester, but just kind of an important thing to remember as we go forward. Okay. So one more step. Like I said, I might have kind of hinted at it, but if we are starting to measure distances to galaxies, what's going to be our final step on our ladder?
Redshift.
Yes. So our last step is the Hubble law. If we can measure redshift, we can use the Hubble law to get a distance. So this is kind of just visualizing that on this plot. Kind of what the idea is for different galaxies, we can measure a spectra. We can look for specific emission lines in those spectra, or I guess absorption lines, as they're being shown in this GIF. But when we get that, we can get a redshift based on how much those lines are shifted and plot that as a distance, use that to find a speed and then get a distance using Hubble's law. So that gives us the distance to the most furthest away galaxies. Although it's not linear and you do have to actually take in a lot of cosmology to get it if you're looking at things over a redshift of 1 or 2. And a few little kind of rules of thumb that I like to keep in my head. If someone says z of 1, that's about half the age of the universe, so that's about 7 billion light years away. If you hear z of 2, that's about 10 billion light years away. and then you get like Z of 8 is like Z of 6 and Z of 6 to Z of 8 is like very high redshift, but it's all approximately the same in terms of distance. Is there a puppy?
Yeah, sorry, that's my dog.
That's a good thing. Sorry. I like animals. We're also probably gonna end early today unless folks have any other questions, because my main goals for today were just to kind of review our 170s, and I think we hit up pretty much everything I need to hit. There is one step I didn't include, or a couple steps I didn't include, but we talked about standard candles. What's the other standard object we might use? It's not a standard candle.
Standard siren.
ruler.
Sorry, I heard two things.
Siren, standard siren.
Siren
Standard ruler.
and standard rulers. So yes, sirens I think are kind of new-ish. So I was prepared to hear that. But yeah, we can also use standard yardstick, standard rulers. So some people think, we'll talk more about H2 regions, which are kind of star-forming regions, that those might all be about the same size. If you know the angular size and you know the actual size, you can find a distance. Sirens, I think, are more with like pulsars and other objects where there's some sort of periodic variation, and you can use that along with, again, the expansion of the universe and light travel time to figure out sizes. Oh yeah, sizes, because you're looking at how it rotates and where the how different it is, and use that to get a distance. So we've got mostly we use standard candles, but there's also standard yardsticks, and there are standard sirens. It's really interesting to think about as LIGO keeps detecting more and more things. We might get like another option with like somehow standard gravitational waves. It's a little confusing. I don't fully understand it, but there are ways that we can use that to maybe calibrate distance for at least some things. Yeah.
Would we be getting like a standard gravitational wave from type 1a supernova? Because if they're standard candle, then we would sort of assume they're at the same mass. So could we be getting standard gravitational waves from those?
So this is really beyond my area of expertise. I think the idea is more, since when we measure gravitational waves right now, the big one that they're hoping to turn into some sort of standardized measurement is the black hole neutron star mergers, because those have both a gravitational wave signal and a luminosity. So you need a multi-messenger thing. I don't know how much like the type 1a supernovas really, they don't produce gravitational waves that we can measure now. Maybe someday, maybe Lisa or something in the future, but with LIGO as it is now, it cannot measure it. And then the black hole mergers don't have a luminosity signature, so we can't compare that to a light source. But with the black hole neutron star mergers, you get the actual gravitational wave as well as a wide range of fluxes from gamma ray to infrared. So you can use how those two things compare. They're hoping they can use how those two things compare to get kind of a standard gravitational wave kind of object, I think.
Could you get that too with neutron star merger?
I am not sure that I'm not sure. I'm gonna end it there. I think as long as there is a gravitational wave and a flux, I think there's a possibility. I don't know the situation with neutron star mergers very well. A little, like, sorry, I just have to say, I'm very happy. When I first research project at Wyoming was semi-related to LIGO, so I got to feel kind of tied back because we were making something called the census of the local universe, where we were looking for every galaxy that could trigger a gravitational wave detection. So all the ones that would be in a certain volume from us. And once you know that, you can take the giant LIGO sky bananas and you can narrow down the area on the sky that the wave could have originated from, because it can only come from a nearby galaxy. It can't come from a distant source. So it decreases the area on the sky you're looking by a factor of 100, which is cool. Anyways, so the last thing I wanted to do today, which, yeah, we're ending early, but I will stay around if people have questions about anything, was to discuss a little bit about the photometry project because I was able to get it fixed and running. So on Canvas, there's going to be a new file that has the updated version of this. I took off the old one. It's very, very similar. The only thing that's different is that there are a little bit of extra instructions around downloading the programs now that I have a computer that doesn't already have 100 programs downloaded on it, so I can actually test things. So if you have a Mac, you're going to need to download this. It's free, it's easy, it's not going to hurt you, I promise. And then after you download Anaconda, there will be some more steps to go through to actually get things to work. And I spelled apply wrong, so that's cool. Working in latex is always a joy. Once you do get it working, I'm going to stop my share just for a second so I can share a different screen. I'm just going to do this. Okay, so the Anaconda Navigator will look something like this, hopefully, when you get it installed. We're going to be using Jupyter notebooks. So this is the only thing you'll need to get under there. Sorry, is this one over here? There'll be some instructions with stuff you'll need to do on this page, including a little bit where you'll need to install a specific channel. This is where I was having issues. I think it should work with the instructions I'm giving you. Fingers crossed. And I think it should work for everyone. This is not specific to Mac. It should work with both Mac and Windows. But the big thing is you'll have to search for a few packages like photutils and AstroPy, this one, and then click this little box and it'll say apply, and you can do that. It should load. Where I was having an issue was that I could not get photutils to show up. And photutils is going to be really important. So if you try to run this and you have that problem, please let me know because that means I did something wrong. What's fun is that once you do get it up and running, you get these really pretty, Jupyter notebooks are really pretty. They're a really nice way to program. So this is one that we'll be working with where you can type in code in these little cells, and then it'll run the code with what you told it to. And so I just imported all the programs we will need for this project. And then you can do nice things. And you can also type text, you can do code or text. So this is what we'll be using throughout. And you can make pretty galaxy pictures. So this is one of the galaxies from my data set in 24 microns, and we'll be doing this. This is kind of a preview for a couple weeks from now. We'll be using these kind of Jupyter notebooks to try to get data. So I'm going to, our first coding day, I think I said this last time as well, is not next week, but the week after. Not here. So not next week. This is all still kind of discussion-y stuff. But the September 8th, we will be doing a coding project. So I will need you to be ready to use Jupyter notebooks by September 8th. Downloading programs can be more difficult than you might expect. So I'm going to encourage you to try to do that. It's step 2 in the photometry project. If you have time to try it this weekend, great. If not, sometime next week. That way, if you run into issues, you can let me know and we can fix them before we get to class and then no one's code works. So this isn't, I really do want this to work when we get to it, and we'll be using it a lot, like all of these next few things. I don't have one for that yet, but I'm working on it. But this is all coding stuff, and then it'll also make it possible for you to do the homework project fairly easily. So And just to stress it again, I am asking you to download these programs, but if you continue in astronomy, it'll be useful to have these. So it's nothing that'll hurt your computer. None of these files are overly large, I don't think. And it'll be stuff that you'll use if you do any astronomy research again. So I hope that it's not asking really much. I think it will actually be something that'll be useful for you. So that being said, does anyone have questions on any of that? Okay. So next week, we're gonna really actually start digging into the kind of history of the universe type of things. As I guess the last thing I'm gonna say, sorry, just so I can know that you guys showed up today, in order to get your participation points, there are 2 little discussions I'd like you to complete that just kind of review what we talked about today and build on the readings. So if at some point you guys can just answer